audience, now we have among us the research person, Professor Dr. Devi Prasad Priyavrata Acharya from NIT Rourkela, who is going to deliver upon the topic clock management in SOC. So, dear audience, kindly allow me to introduce to you all Dr. Acharya. Well, Dr. D.P. Acharya is currently working as professor in EC department at NIT Rourkela. He received his PhD degree from NIT Rourkela in VLSI signal processing and has industrial experience in ASIC and FPGA design for wireless systems at Tata Exley Limited, Bangalore. VLSI system design, Wipro Technologies, Bangalore. He has developed analog and mixed signal IC lab, IoT lab, PCB lab, and reconfigurable system design at NIT Rourkela. He has completed many government projects as well. Well, he has many publications in reputed international journals as well as conferences. Many MTech and PhD scholars are awarded under his supervision. In addition, his research interests include VLSI design, embedded systems, analog and design, IC design, PBT aware and self-heating IC design, embedded systems, industrial IoT, intelligent IoT. Well, he is also the member of IEEE USA and life member IETE. So without any further delay, I would like to request Dr. Acharya to initiate the session. Sir, please.
Thank
Good
you,
afternoon,
madam.
sir. Good afternoon, sir. Thank
Good
you.
afternoon.
Yes, sir.
It's very nice to have a good interaction with people over here. I have chosen a topic of clock management for SOC, which is a non-trivial topic among the people in academics and students. So without further introduction to the topic, I should share my slide. Okay?
Yes, sir.
So, that's it now. I have shared my entire screen.
Yes, sir. Visible, sir.
Thank you. Thank you, madam.
Pleasure, sir.
So I once again wish a good afternoon to each one of you present here. I was telling you that people talk of system on chip. When people talk of system on chip, it means many components are there on the system. And that itself is put on a single piece of silicon die. So when I call many components are there in the system, the components, individual components or parts may be hard IP cores or maybe soft IP cores realized on any platforms. Together we put it on a die. So definitely if we break it down, it becomes some combination of sequential and combinational logic along with other dedicated analog blocks. When we talk of SOC, this SOC consists of digital blocks, analog blocks, and also mixed signal blocks. What happens? Analog blocks are dedicated blocks, but the majority of SOC is actually the digital blocks. Digital blocks can never be imagined without sequential circuits, without registers. So when we have such digital blocks, these digital blocks must need a clock to operate. This clock is everybody knows what is a clock. It's a very easily perceived one. Now we will look into the issues or the requirements of clock, its management, stuffs on a system on chip. I have divided my presentation into basically these 5 parts. What is the need of clock? What is generation and distribution of clock? Clocking for energy, clocking in processors, multiple clock domain issues. I have put this outline keeping in view of the requirements of designers in industry. My presentation targets to creation of efficient designers for semiconductor industry, in particular issues. So let us go ahead. What is the need of a clock? It's very simple. Sequential circuits are there. They can't operate without a clock. Looking at a very layman's perspective, if I don't have a watch, then I cannot really work. Then you may say that, why do you need a watch to work? Yes, I don't need a watch to work. If I am a laborer in the field, still I need a watch. You may say that no, most of the laborers, they don't have watch. In the fields, they don't have watch. They have the watch of nature. They see that it's morning, they see it is evening, they see it is noon, so accordingly they work. They see that at this period of time we should do this. So nobody is working without a clock. Even if the animals also, they don't work without a clock. They have their biological clocks. A dog knows when to get up. A bird knows when to sing. A bird knows, an animal knows when to eat. So everybody is having a clock in one form or other. Hence, how can a circuit really work without a clock? It has to have a work clock. And clock is very, very fundamental to our systems. Let us look at it as a very beginner. The heart of synchronous digital systems. All the events are controlled by the active age of the clock. Sometimes the clock frequency is synonymous with throughput and performance. I believe you understand throughput of a system. How many outputs? What is the giving the output, throughput, performance? That's why the designers need to understand the trade-offs and choose a distribution methodology that meets all the design goals. Friends, I give you a freedom. Please feel free to discuss with me if you find anything is not or anything is causing a concern for you. So please feel free to discuss with me then and there. This is a very popular Hoffman model of a FSM, finite state machine. Everywhere we have FSMs. You people know what are FSMs. You know Millet FSMs, Murray FSMs, many FSMs. Simply putting into a picture, we have combinational circuit and storage elements. You can see here, the clock is very much there. It's very much there, clock. If I stop the clock, the entire circuit is meaningless. You don't have a control what is the output of what input, nothing is known. So that is why you call it its heart of our system. Let us see the clock frequency of some historic computers and supercomputers. Many of the computers you will know, vector processors, mainframe computers, microprocessors, like, see, people are aware of, very much aware of this Motorola 680 0010, so 1985 microprocessor. So it is working at 16.7 megahertz speed. People must have known about this Cray, very old processors. So these are historic things. I should not spend much time on that. To give you a feeling of clock frequency of some computers, processors. Why do I talk of computers, processors? Because our systems are nothing but these computing systems, processing systems, and then some other things added to that. Coming to a next one. This is somewhat very recent, it's not that old. If you see, all of you work with such processors, i7, 4.4 gigahertz, built on Intel's 10 nanometer super FinFET, i9 10th generation processors targeting towards 5 gigahertz, Intel's gaming laptops, games need high frequency. When you tell high frequency, there are perceptions go different to different people. Designers actually work down to a register level to talk of a frequency. So when you give me some task to be done within 1 hour, I break the task into small tasks, then finish each task within 2-3 minutes, 2-3 minutes like that. So to me, the period is less. The executor of the task needs less period and hence high frequency. Let us go ahead. Parameter understanding of the clock. All of you know what is a clock. It's a time period. The most ideal clock run here. The time period. The high period. Then duty cycle. W by T, percentage you can express. Rise time, fall time. People have different definitions of rise time. Somebody says 10% to 90%. So I say that no, it's from this to this, from this to this. But see, the real world is not so obedient, so beautiful like this diagram. Real world is little bit notorious. So when slowly notorious things come, like that skew is there. It's one of the most talked parameters of the clock, skew and jitter. What is skew? If I have a design, I have a flip-flop here. This is the clock to the flip-flop. Another flip-flop. And some in between combination logic is there. This flip-flop output is going here, this combination output is going here, here, here. What I expect is that the same clock is fed to both the flip-flops. Now, I am thinking that the clock's arrival at this point and this point are quite instantaneously set. But this path cannot, maybe so, it may be very long. So that the clock arriving here, if I call it as clock 1, if I call here it is a clock 2, so there is a delay of arrival, you can see from here to here. So we say reference clock, this is reference clock, clock 1. Clock 2 is the received clock. So there is a delay, and that delay I term it as skew. Delay, spatial delay, I call it as a skew. Similarly, I have different measures for skew. Then people talk of positive skew, people talk of negative skew. All of you must be knowing. I believe all of you are quite smart in digital design to know about positive skew and negative skew. So with that assumption, I proceed. Then something known as a jitter. Jitter is that whenever this clock is arriving, this clock is coming from a source here. Here is a source of the clock. The output of the source, the age of the clock may arrive little early, maybe little late. So there is a fluctuation in the arrival age of the clock. And that fluctuation, peak to peak fluctuation, is termed as jitter. Left side jitter minus, right side jitter plus. This basic definition of clock, jitter and skew. And see here, I was telling you the world is not so ideal. If you see the real clocks, if you have ever seen in your CRO or DSO anywhere, looks like this. There are hodgepodge here, there are disturbances here. But I know, I always say I ignore all this and tell that it is my high. I tell this as my low, this as high, low. So this I do an approximation. I believe this is constant and take it high, this as low. But what about this? Skew I cannot avoid. Skew has to be there. Then you can see sometimes this rising edge is coming here, sometimes it is coming here. So there is a definite window in which the clock arrival age is uncertain. So this clock uncertainty is there. Jitter and skew together account for the uncertainty in the clock. Now you say that, sir, jitter is uncertain, I am happy, I could understand. What about the skew? Why it is uncertain? Skew is definitely uncertain because with different paths in interconnections, the widths, the lengths, the environment, everything affects the propagation of clock signal here. Actually, it is the flow of charges. So how much time it is taking to travel from here to here is somewhat uncertain. It may be looking certain to some extent, but truly speaking, somewhat it is uncertain when I talk of a great SOC. So such uncertainties I am going to accommodate. How to observe the clock uncertainties? Skew, jitter, uncertainties are there, and I am going to design my clocking system for my entire SOC so that the uncertainties will affect less to my system's performance. That is what we talk today. The trend is that the clock distribution will become progressively difficult. Why? Because there is a mismatch of load. When there is a mismatch of load, then definitely this uncertainty will be further enhanced. There is variation in the process. Process, I mean say manufacturing process. I mean it is fabrication process. There will be fluctuation in the supply voltage. There will be also variation in the temperatures. Why temperature variation? You say, sir, I have taken a chip, I am keeping it in my office, my industry, my room. Where is variation of temperature? Temperature variation is not there. So when I talk of temperature variation, I mean the same device that is meant to be used anywhere in the world. I am a global manufacturer. I am not a manufacturer only to sell in my locality only in one season. I have to sell across the seasons. I have to sell across the geographical boundaries. Hence, there has to be places where minus 40 degree like Siachen Glacier is there. It has to be sold at Vladivostok in USSR, Russia. It has to be also sold at deserts like Thar Desert, Sahara Desert, everywhere. So the temperature range varies from minus 40 to plus 50 degrees centigrade. Over such a wide range of variations, there will be variation in the clock uncertainty and it becomes more uncertain. So in such an uncertainty, designer has to work. Designer has to give a design that will be robust against such uncertainties. That is what we target today to discuss. The clock uncertainties will occupy increasing portion of the cycle time. So the ability to reduce impact of these uncertainties is one of the most important properties of the high performance system. You may be knowing that the same digital systems you are studying, when you study in BTech second year digital electronics class, you study same latch, same flip-flop, counter, register, same memory. And not only today, you are studying that thing when you are studying your MTech or course, when you are doing PhD also, you are studying the same thing, working on the same thing. So at different levels, you are studying those things. Not only that, people studied these things 50 years back, 10 years back, 5 years back. Today, same thing will be taught tomorrow. Now what is happening is that the circuit elements remaining same, the circuit complexity is increasing, density is increasing, the need of performance is increasing, the technology or feature size is decreasing. So at all these times, your circuit receives the same clock, but the performance keeps on changing. Hence, high performance system designers are very, very particular about their clockings. And you would be very much happy to know that today, just functionality is nothing. Timing is everything. If you don't meet timing, then your systems are as good as ineffective or faulty systems. And timings are kept only by clocks. Let us see here the clock generation and distribution non-identity is introduced by jitter. So we have seen jitter is nothing but temporal variations caused by temporal noise events. There is cycle to cycle jitter, short-term jitter, there is long-term jitter. People call long-term jitter as wonder, a different name. Mainly characteristics of the clock generation system. So jitter is affected by, or jitter is detected by clock generation system. The skew, it is the time difference between temporally equivalent or concurrent edges of two periodic sequences caused by spatial variations, I have told you, manifests as CSC to CSC fluctuation, clock arrival, same time instant. So characteristics of clock distribution system. And this skew, see, the important thing to note here, it is characteristics of the generation system. This is characteristics of clock distribution system. Now let us first talk about distribution, then we'll talk about generation. When we talk about clock distribution system, within a system, the distribution will happen, it will be generated by a crystal oscillator. After some delay, it will go through different sections, gates to boards. So boards means PCBs, printed circuit boards. Your system is like one cabinet. If you have happened to visit telephone exchanges, you must have seen the telephone exchange is having cabinets like this. And in these cabinets, you have your cards like this. I am showing the outside of that. PCBs. So PCBs are introduced here. 1, 2, 3, 4 PCBs are there. Similarly, PCBs are here. And you need to communicate between this PCB and this PCB, this PCB and this PCB. So many communications should be there. And system will generate clock somewhere. In some PCB, clock generation will be there. It will be distributed to different PCBs. So that's what we call boards. On the board, there will be a shaping and powering one, logic chip one, RAM chip one, processor chip one, on a single PCB here itself. So different chips are there. All these chips will get clocks. Then tuning of the clock has to be there. From board one clock on, there is tuning point. tuning point, different clock tuning has to be there. So there will be early clocks, normal clocks, late clocks. So we need some normal clocks to operate, some clocks delayed, some clocks arriving early. So such tuning has to be there, and it is for a system. Now this entire system today is sitting on a single chip. We don't have a cabinet. This entire cabinet is becoming a single chip. And we call it as your SoC, single chip. So system on a chip. The same principles will apply here also. I am talking regarding few clock distribution methodologies which are very popular. Popularly, there are two clock distribution methodologies, and there is third one is there, which is a hybrid of these two. The first one is a clock tree mesh. So this one you can see it is a clock tree mesh. Tree, just like leaves are coming out of tree, different leaves. So similarly, it is a clock tree. It involves a dense maze of shorted wires to distribute the clock to every corner of the dial. I can say to every sequential element like a flip-flop or a latch. So if you want to give the clock to every corner of the design, then you need mesh drivers. Why do you need? Because you have to drive a lot of capacitive loads which are started to effectively ensure that clock arrives at the same time along all points in the mesh. If I see clock is going from here to here, this way it is reaching here, it's going here, going here. So I ensure that every place it is reaching approximately at the same time. Then there is another distribution methodology which is on a single point CTS, clock tree synthesis, single point. So the point of divergence lies with the clock source here itself, diverged. So this will allow the clock gates to be inserted strategically at the source to allow clock to be gated in order to save dynamic power. So here there can be 10 to 30 stages of clock buffers should be there. They drive. Then there is another way is multi-source CTS. It's a trade-off between clock tree mesh and single point CTS in terms of its metrics. So it will involve a global distribution network in form of a sparse mesh or an H tree with tap points strategically inserted at different locations. We'll be very clear about this H tree right now. Let us see the performance of these three systems. The clock tree mesh, the clock skew is low here. Single point clock skew is high. Routing resources are more here, routing resources are less here. Clock power is high here, clock power is low. Impact of OCV, OCV means on-chip clock variations, on-chip variations. Minimal here, high here, moderate. So people choose this strategy, multi-source CTS. So there has to be a balance, there has to be optimization between these two to arrive at this multi-source CTS. Designers in industry choose this. Now let us look more into the clock trees. Here I have taken, it's a very old one, 1988 IEEE. And this is your, you can see it's a RC matched tree. RC matched tree means, what is RC? RC means R is the resistance, C is the capacitance of the path. You can see here, there is a PLL, it is giving out a clock going here. From here, it is going as a driver here, from here to here, here to here. So from this point, if I see any logic block here or here, I am taking two typical places. You will see the RC delays are matched. See here for this this point, if I am going in this path, so this, and from this point, if I am going in this path, see, this corresponds to this corresponds to this, corresponds to this. It's RC delay matched. And you can verify it between any two logic blocks who are getting clocks from this center. You can say this as origin, center, starting point of the clock. Of course, the clock itself is coming via a route from its source here. So this is what is known as a RC matched tree. Here it is a grid. You give here, it will come here. So it is routed, and everywhere there is minimal delay. These are typical distribution methods. So RC delay matched clock distribution topologies. There are different topologies. See, RC delay is this one, but RC delay topologies are many. This is a binary tree. Here. See, if you see the path here to here and path here to here, they are same. And there is another popular, this is very popular H tree, very popularly used. H, shape is in H form. So from here to here, if you go this distance and this distance, they are same. Any two distance you take, their RC delay is same. Similarly, there is X tree. From here, you see all the points are same distance. Then there are also arbitrary matched RC delay trees. Arbitrary. From here, this distance is same as this distance. So people try to match it arbitrarily. So these are the topologies of RC delay matched clock distribution. Now, I am talking of very important thing. This is about distribution. Now, why clock is so important? Because clock power can account for more than 50% of the total power dissipated in the design. The choice for clock architecture will have an impact on total power dissipated in the design. So now we are talking of the clocking for energy. It is very well known that SOCs are designed for performance. Performance means first is speed, second is power, third is area, and fourth one is cost. When I talk of clock, people generally relate it to speed. Generally. But people forget that clock is highly related to power consumption. This is very, people take it very casually, that they don't forget that clock is much related to power consumption. So how to do clocking for reducing the power of SOC or increasing the power performance of the SOC? The same concept is used by many processors. When you talk of Intel's Atom processor, consuming very low energy, low power. So such processors are using specific clocking strategy to reduce power, because clock itself is one of the most active signals. Now, there will be system issues if you increase the clock frequency. We have a low skew requirement. We need to do deeper pipelining. Pipelining means something doing in a very back-to-back fashion that will increase the throughput of the system. So increased clocking energy will focus on energy minimization. We'll see how different methods of energy reduction are there and clocking strategies, how it helps in that. Let us look at this fundamental expression. Those who have studied about IC design, you must have studied about this equation. Switching energy is dependent on alpha 0 to 1 transition, capacitive loads, swing voltage, VDD. So alpha is the probability of 0 to 1 transition. Ci is the total switched capacitance at any particular node I. V swing is voltage swing at node I. Supply voltage. N is number of nodes. With increase in number of nodes, your U switching will increase. But one of these things you cannot avoid. This has to be there. But you can see there is a small factor sitting here. This factor looks like a negligible factor, but this is one of the best culprits. The energy is best reduced by scaling down VDD. Generally, scale down that. But this also means performance degradation. When we scale down VDD, there is somehow performance degradation. Other trade-offs are there. Hence, clock is actually related to the activity alpha. So low swing clock techniques, circuit techniques are there, clock gating techniques are there, dual edge triggering techniques are there. Here we will not talk about dual edge triggering. We will restrict glimpses of these two techniques, low swing circuit technologies. We will restrict, and I am not going to go too deep because clock itself is a vast topic. People do a lot of research in industry. Of course, people in academics, they don't do research on this. I have not seen people doing because they don't face the problems. Problems are faced by the people in industries. So they pay much attention to these clocking strategies and clocking techniques. Of course, that doesn't mean that people in academics, they don't do. They do it. But most of the people in industry focus on this. Let us see at some of these techniques. I am not going to go to details or all of this. I will tell you only for some of this. First, you see low swing clocking. Now, what do you mean by low swing clocking? If the clock itself is traveling from 0 to VDD or ground to VDD, if my VDD is 1.8 volt, then there is a full swing, and full swing means there will be sufficient amount of time needed for charging, and again there will be, if you allow the stops to discharge, means say suppose at one node I am allowing my node to go from VDD to ground. That means the charges are flowing from that node to ground and my power source is getting discharged. So when it is getting discharged, it is consuming power. One of the good tricks is that do not allow the clock to swing full rail to rail. Allow the clock to swing less. So if the clock is swinging less, then power consumption is reduced. You can see here in a circuit here, you can see we are having from ground to this value. Then from this value to this value, we are not allowing from ground to VDD swing. The N transistor, P transistors, their P is swinged here, N is swinged in this region. So N transistors are given this. So generally this is a low swing clocking strategy whereby I have a clock here, I have an inverter giving to CNT here, then CPT, CPB, CNP. So this is what we do, so that the objective is not to understand this circuit. The objective is to see that I am able to manage the swing between these two. Here. No requirement of ground to VDD. So when we have a half swing clock, there is a 50% power reduction. Of course, we pay some penalty for drivers. There is another strategy. Say low swing clocking strategy 2. So here we have a PMOS. We don't allow the PMOS fully turn up. This PMOS is not allowed to fully turn up. If it turns off, so here this is again reduced clock swing flip-flop. I'm not going to explain you the details of the design. In fact, many papers are available in this design, so you can refer to that. Here you see we have these are the clock drivers. So again, it is a flip-flop that is designed with reduced clock swing. Strategy 3. So here, N only clock transistors. It is a master latch example. Master slave configuration of a latch. All of you must be understanding that this is a latch configuration. This is the pass transistor. It's the clock driving the pass transistor's gate. Similarly, clock here. Clock bar. We are putting the NMOS transistors here, N1 and N2. So N only clock transistors, N1 and N2, improve the pull-up on SM, on this node. They improve the pull-up. These are only strategies by which we make our clock to swing very less. Then comes one of the important techniques, all of you must have heard of it, it's a clock gating technique. Clock gating, see, we are doing a time box without any gating, straight away clock is going here. Here we are getting the clock. So this is a global clock gating. This is used to save clocking energy when data activity is low. So if your data activity is low, then clock energy is saved. See, am I audible to you people?
Yes, sir. Yes, sir.
Because when that side it becomes completely silent.
No, sir, it's fine. Everything is fine, sir.
Okay. So I apprehend that the network connectivity has become slow. Anyway, thank you very much for responding.
Okay, sir, it's okay.
So what is happening? People generally, when we talk of clock, people think of only speed. They forget about the power also. So clock gating techniques, all of you know that it is used for reducing the power. Then something is global clock gating, another is local clock gating. Local clock gating means shut down the region where you don't want to do any activity. Global means right from the beginning, the system is there. From the beginning itself, you do getting here itself, and it goes everywhere. Local means wherever required, there you get it. So you don't need to get it at the source of the clock itself. Wherever required, you have to control the clock locally. All the places there is no need to clock control. So that's how local clock gating was one of the efficient techniques that is used by SOC designers, and SOC has much of relevance with respect to local clock gating because there are different blocks in SOC. Each block has a performance required at a different point of times. The activities are different. So the designers, system designers in the SOC, they do local clock gatings to save power. Now let us look at the clocking in processors. See, there are many microprocessors, and when I talk of microprocessors, all of you talk of Intel fast. Intel comes as a fast one. So I have given Intel as fast. Now Intel means there are varieties of processors, 8085, so many 8086, so many architectures. There is 386 machine, 486 machine, so many machines are there. But you started talking of complexity when it came to Pentium. Pentium is Intel's 32-bit architecture first. Intel architecture 32 bits, then 64 bits, then Pentium 4. There are other processors, Sun Microsystems, UltraSpark 3. So there is alpha clocking, IBM processors. We will not talk about all. We will talk about only few. Well, this is a typical system, very simply depicted for Intel architecture 32, Pentium Pro. Here is the clock generation, then there is a buffer, delay lines are there, then you have this left side, we call it left spine, and this is the right spine. Clock is coming this way, here. Then going to the core of the processor. From the right side, it is coming this way. This is done with the purpose to reduce the skew. So you call it D-skew control, and there is a delay SR. Delay SR will control this delay. If you need more delay, then this will be programming this. This is the external clock, this is the feedback clock going from here. And this is your core of the processor receiving clock. So this strategy is used in IA36 Pentium Pro for clock distribution network with a D-skew control circuit. What do you mean by D-skew control? D-skew control means I am interested in reducing the skew. So how do I do? I do by controlling this. By controlling these different points of control I have. Now we can see the first Intel architecture 64 microprocessor. Here is the clock source PLL. Then clocks are traveling here and here. You have the D-skew. See, this one is looking like the D-skew drivers. Then you have PLL, the core clock will be there, then the reference clock. So such is the architecture followed there. You have Pentium 4. Pentium 4, there is a bus clock, dock, then there is a bus clock here, bus core clock, data clock. So many clocks are there. So here you can see the core clock going here, clock enable generator, clock enable distribution and sync, clock enable distribution and sync, going to both the sides here and here, here and here. Then there are macros. The core PLL, we'll talk about this PLL also. So core PLL giving to core clock distribution here. Then IO PLL will be there for IO clock. See, when I talk of any processor, I have cores and IOs. IOs are there, input output pads. IOs are there. Core is there. Core is having a different clock and IOs are having different clocks. So there is core clock distribution, IO data clock distribution. Then you have D-skew state machine controls are there. Then you have master flip-flops data. So data clock is there, core clock is there, then IO clock, IO feedback clock is there. So many are there. If you see, the clocking becomes very complicated. You have different clocks and their strategy is different. And you talk of higher versions of Pentium, the complexity increases further. The logical diagram you can see here, there is a PLL, phase lock loop, 3-stage binary tree for clock repeaters, domain buffer, there is phase detector, then local clock macro, sequential element, local clock macro, sequential, local clock macro, sequential elements. So these control the clockings and then sequences. So there are domain buffers also there. There is distribution network, then buffers available. This is what is a logical diagram of Pentium post clocking. Now I talk of alpha microprocessors clocking. They use clock grids like this. This is one topology, this is one topology, then another topology. They use different topologies for clocking. PLL is giving through a grid distribution, then this GCLK grid. Now, there is a term GCLK is there. What is that GCLK? GCLK stands for global clock. Global clock. What is global clock? Global clock means this is a clock with minimum skew. If I allow my clock source to be connected to this global clock network, then the clock wirings will go through this grid only, nowhere else. And this grid is such beautifully arranged that between any two elements, logic elements, the skew will be minimal. So that is what we call it GCLK, global clock grid. We allow it to land onto a global clock grid, then it gets rotated. It is something like this. You have your farming fields, you must have seen. There are layers. Suppose you are doing some cultivation. Say, you can say, what you can say that you are doing banana, or say some cultivation you are doing. Then you don't give water to every row, some 10 acres of land. Do you give water to every row? You put it at one end. Then once the water comes there, automatically the water flows to the rest of the system. Some 2-3 strategic points you only give water, and water automatically gets routed to each tree. To root of each tree it goes. Similar is the stuff here. So this is the clock network. You have a DLL, you have DLL, you have a DLL here, then NCLK here, GCLK grid is here. So this was some examples I was giving you how in different processors the clock distribution is carried out, and accordingly people apply the same to different SoCs. Coming to another stuff known as clocking scheme. Most of you must have heard of this. Single phase clocking, dual phase clocking, multiple phase clocking. People use this. So this is single phase, means one clock is going everywhere. Here you have two clocks, phi 1 and phi 2 are going different places. Some 50% this one, 50% this two. The advantage is that you will have most of the times the clocks are non-overlapping. There are other requirements also, clocks. Similarly, you have multi-phase clocking. So many clocks are given the system. So these are having design advantages. Based on that, people choose the clocking scheme requirements. So this is a case of local generation of two-phase clocks used in IBM's 390G4 machine. This is a global clock. From there you have clock 1, clock 2. The circuits used are like this. So I did not go to details of the circuit. These are simple digital circuits you can know. Global clock is going here. We generate clock 2, clock 1. So they are non-overlapping clocks. So non-overlapping clocks gives us speed advantages. They give us other advantages like they reduce the chances of metastability. Many things are there. So clock generation, we can say that we do via primary global routing resources, global clock distribution network. We use global buffers. We use buffers at top center, bottom center. We have dedicated clock input pads. We have input to global buffers from pads or from general purpose routings. This is what. Now, I will pay my attention towards a programmable ASIC. if you you must have heard of FPGAs. So FPGAs also they use this global clock distribution network. See, here the clock is coming here and getting routed through this. So this is global clock spine everywhere. Global clock rows are there, global clock columns are there. In FPGAs, it is very much there. So I have shown you a typical from your very popular Spartan 3 architecture. How clocking is there. You can see here. This is the top spine. Here is the bottom spine. Right spine, left spine. So this is how the clock distribution network is here. Everywhere almost same. And what we are doing is we are using BOFG mocks. BOFG means it is global buffers. Global buffers are there. These are global buffer mocks. Global clock inputs are given. If I put my clock to any of these global clock inputs, then it gets routed through these available networks. This is from the simple Spartan 3. Now you must be seeing DCMs here. All of you know what are DCMs. Those who have worked with FPGAs, DCM means digital clock managers are there. This is very interesting that digital clock managers in FPGAs, whatever they do, they are already fabricated IP cores, hard IP cores available inside FPGAs. They manage the clocks. So there are different clock managers at different corners, different locations. We have to manage by designing our own systems. The purpose of showing this DCM here is to make you aware of what are the requirement of management in clock management in systems. So clock management in programmable ASIC like FPGA, this is how they do. DCMs will be there, then CLBs will be there, then multiplier, so many things, and DCM will manage different. So digital clock manager consists of phase shifters, consists of frequency synthesizers, DLLs. These are the three main parts. So phase shifter job is to shift the phase of the input clock. Clock input is there. It can shift by 90 degree, 180 degree, 270 degree, something like that. Whereas frequency synthesis means it can give you a multiplied frequency with 180 degrees phase shifted. Then DLL lock loop will give you stops like the synchronized clock. It is one associated with what each clock buffer eliminate the skew between the clock. So if you are routing your clock through these DLLs, it will eliminate the skew. Means skew between the input clock pad and internal clock input pins within the device. It can drive global clock networks. Clock edges will reach internal flip-flops 1 to 4 clock periods after they arrive at the input. Because this period of time they take it for synchronization. Provide or delay, provides control of multiple clock domains, has minimum clock frequency restrictions. Well, I'm not going to say more about DLLs. You have seen that this is input clock, this is double the frequency, then frequency division by something, then duty cycle correction, 90 degree phase shifted, 180 degree shifted, 270 degree shifted, duty cycle correction, true. So those things are there and I should not talk about that. Digital frequency synthesis, they do. You have input clock here, then multiply by some factor m divided by n gives you clock effects. With this idea of distribution and some management idea, we will pay our attention little bit towards clock generation in SOC. See, one of the sources for generating internal clocks is PLL. PLL stands for phase lock loop. What does it do? You give clock with, say, some 10 megahertz frequency. The PLL will give you a clock of 5 megahertz or 20 megahertz or anything required. So PLL is used as a clock synthesizer. PLL is also used as a clock synchronizer between the input and output clocks. And PLL's output clock is used by a source clock by clock generation block. You have divisor circuits and necessary glue logic to generate the required clocks. Typically, this is the diagram. You have a PLL given to your clock generation system that is used by SOC. SOC here. Generally, clocks are generated by your crystal oscillators. You have a temperature TCXO, VCXO. You must have heard of this. Temperature controlled crystal oscillator, voltage controlled crystal oscillator. You have Oben controlled crystal oscillator. You have your VCOs, voltage controlled oscillator. Many are there. So they are used. Crystal oscillators, VCOs, many are used for clock generation. Then you have TCXO, means temperature control compensated, crystal oscillator is there, there is a compensator. So many are there used for clock generation. This is one of the most vital things when we talk of clock, we talk of PLLs. And PLLs one of the most widely stops used in SOC. I really do doubt any PLL SOC is there which doesn't contain PLL. Anyway, you can clock small fellows as SOCs, but I really doubt any block is there, SOC, which doesn't have a PLL. Many people would be knowing PLLs. We are not going to talk about PLLs today. We are just going to introduce that. PLL itself is a vast topic. There are volumes of books, hundreds and hundreds of papers written on PLL, thousands of papers written on PLLs. There are different types of PLLs. There are analog PLLs, digital PLL, all digital PLL, soft PLL, CMOS PLL, so many types are there. So PLL consists of a phase detector, a low pass filter, a VCO. Phase detector, low pass. Sometimes it is a phase frequency detector, low pass filter, VCO. Then you have a clock divider network that goes to that. And there is a feedback path here. It is a feedback system. Negative feedback, you can say. External clock, internal clock. There is this phase shift or phase difference will be decided here, that will be given to low pass filter and VCO. VCO will have a control voltage around which this voltage will be controlled and to generate a different frequency. So based on this phase difference, this will be adjusted here to generate a frequency. So we have dividers in the path that are used for frequency synthesis. It's PL frequency multiplication, phase frequency LPO, then divide by B, clock driver by C. So this will help us to generate different clock frequencies. We call as PLL frequency synthesis. Well, I'm not going into details of PLL now, because PLL, many people are working in PLL. PLL is itself a big topic. We can have some 20-30 lectures on PLL. Now, my objective is to give you glimpses of clock management in SOC. So the last part of the glimpse, which is a multiple clock domain issue. What is multiple clock domain? So it's very obvious that when SOC is there, there are different blocks, and each block is not expected to operate with same clock, same frequency. You may be having a part which operates at some 10 megahertz. There can be other part which operates at 15 megahertz. some other part can operate at 5 megahertz. Highly possible. So if that is the case, then do you feel that all these parts are disconnected? Because F1 frequency part, F2 frequency part, if they are not disconnected, then the data from F1 frequency will be moving to the data to the F2 frequency. Obviously that will be there. So if that is there, then how do I manage? It is one of the most important challenges faced by industry, and all associate digital designers, they very well know this. So friends, I have told you my purpose of this talk is to create professionals for better industrial designers. Also open ideas which generally academicians do not put thrust, give importance. Open up new doors for doing research into that. So one of the things is that multiple clock domain issue. Multiple clock domain, I'll give an example. Suppose the one domain is operating at a frequency F1. Other domain is operating at frequency F2. Data from frequency F1 domain to F2 domain is moving. Then what will happen? Now there are different cases. F1 may be greater than F2, or F1 is less than F2. If F1 is greater than F2, means data is generated at a higher rate and received at a lower rate. So obviously there is a 100% probability data will be lost. You think of a situation like, I always give this example when I try to explain this. Suppose two friends have gone to eat mangoes. One friend is at the top of the tree. He is picking up mangoes and giving it to the ground fellow that you eat. Then you will come back to the top of the tree, you will pick up mango, I will eat them. So the fellow who is picking up mango, he is picking up at a faster rate. The fellow who is eating mangoes, he is eating at a lesser rate. So definitely the fellow who is supplying mangoes at a high frequency, many mangoes will be lost on the way. It will be thrown, it will be non-stored. So because the consumption is less. So similar is the case when data is going from a faster clock domain to a lesser clock domain or slower clock domain. So many of the data will be lost. So how to manage this? Very simple. Both the friends take a basket with them, and the fellow who is picking up mango, he will put the mango, pick up mango and put it in basket. The other fellow will eat it. Once he has finished one mango eating, then he will pick up another from the basket, then eat. So first mangoes will be picked up and stored in the basket, then it will be eaten. Buffer. Buffer will store the information data. If the data is collected at a faster rate and processed at a lesser rate, buffer will be storing that. But there is a limitation of the buffer. The basket has a size. If the fellow keeps on picking for a high amount of period, then the basket will be filled. And when the basket will be filled, then all the mangoes will overflow and it will fall down. Similar case will happen with the data. So that is why the buffers need to be controlled. When the buffer is full, signal must go to the person, please stop. Please don't put more mangoes in my basket. When the buffer is empty, the signal must go to the outside person, say it's empty. You have to do something. So that is why a buffer, which is typically known as a FIFO, it is FIFO buffer, is used when the data travels from a higher domain to lesser domain. So people call it moving data across clock domains. Now the next is the other case, that when the data is traveling from a slower domain to a faster domain. then you may say that there is no problem, because the fellow who is picking up mango is a very lazy fellow. He is picking up one mango and dozing for some time. After that, he is picking another mango. The person who is there on the ground, he is eating fast, no issue. But friends, still then there will be issue. The issue is that the fellow is dozing. When he is picking the next mango and throwing to the other fellow, how does this fellow will know? Only way is that the fellow has to stare at the fellow, keep on watching what he is doing. Then only he will pick up the mango. And when the fellow is throwing, he will take it up. But our systems are not that intelligent like human fellows like you and me, that we finish the mango and still, or even if we are eating the mango and still stare at the tree, what he is doing there. So our systems are not that intelligent. We have to make them intelligent. How do we make them intelligent? By inserting something known as a synchronizer. Synchronizer. The role of the synchronizer means the fellow who is giving the information data has to be synchronized with the fellow who is receiving. So both of them know that yes, my timing is matched. So synchronizations are again done by flip-flops. Friends, again this talking about multiple clock domains, synchronizers, FIFO buffers, it is again a specific topic itself. I am only touching the fundamentals of that to give you a glimpse of clock issues. Synchronizer, good synchronizer design and use will reduce the probability of observing metastable data. What is a metastable data? Metastable data means, suppose you are eating, the fellow has given you mango. Then the mango will hit at you and it will be lost. So metastability means latching the information when it is changing. I can give you an example. I always give this example to students. This is a mountain, hill. See, the drawing is not that good. Please accept my bad drawings. So here is a ball. This is 0 side, logic 0 side. This is logic 1 side. Which side the ball will go? Which side the ball will go? Either this side or this side. So if it is sitting here, then such a state is known as metastable state, and the ball will go to 0 side or 1 side. It depends on from which side the wind is blowing, or some disturbance is coming. Otherwise speaking, some noise is coming. So entirely noise is predicting to which state the final output will be. So that is why I call it metastable. It is not stable, and here the noise is only governing. And as you know, noise is not known. Whether noise is positive to this side or noise is to this side, I don't know. So it is unpredictable, so my output is unpredictable. And such states are known as metastability. Many of the SOCs fail if metastability is not taken care. So to resolve such issues, we use synchronizers for all crossings of data from one clock domain is F1 clock domain here, to other clock domain, F2 clock domain. So at this crossing, we put synchronizers here, data crossing. The popularly used synchronizer is a double flop synchronizer. It's a bit synchronizer. Flip-flop 1 will go metastable, but flip-flop 2 doesn't look at data until a clock period later, giving FIFO-F1 time to stabilize. Limitation is that while moving from fast to slow clocks, data may be overrun. So we can't synchronize watts since beat may not be seen at same time. There are other synchronizers too, pulse synchronizers, watt synchronizers, FIFO synchronizers, asynchronous RAM synchronizers, null synchronizers, reset synchronizers, many types of synchronizers, and this is a huge topic of discussion. Well, good good multi-clock design practices identify different clock domains early in the design, and these multiple clock domains are frequently available in SOCs. We have to partition the design in SOC such that there is one clock per module. This is very, very important. We have to keep the synchronizations to the interfaces only. So my SOC is like this. I will partition, here is one module, here is another module, here is another module, here is another module, here is another module. So these are different clocks. And these boundaries are very clear, crystal clear. And partition design, there is one clock per module. So module 1, 2, 3, 4, 5, 6, 7 modules are there in my SOC, and this module partitioning is done depending on the clock, one clock per design. And synchronization will be done at the interfaces only, wherever there is a crushing. And we have to limit the number of signals which cross the clock domain. Important is that it's not that there are two clock domains, I can allow them to cross as many signals as possible. Because more the number of signals, more will be my synchronization issue. So I have to limit the number of signals which will clock my clock domains, cross my clock domains. So these are important stops for SOC designers to keep in mind with respect to the clock domains. Well, there are different challenges involved in the clocking of SOC. You have seen there is always increasing requirement of speed. Complexity is increasing. People want high-end video processing, high-end gaming in the same device, same chip. And there is a huge scope for optimization, in fact. How to do the partitioning optimization, then there are many scopes of optimization. In the optimization can be done through different optimization techniques. Then of course, there is a changing industrial problem with feature size. Feature size was 90 nanometer. The design was there. Now it has changed to 45 nanometer. It has to be redesigned. It has changed to 22 nanometer. It has to be redesigned. 10 nanometer redesigned. From CMOS to FinFET, again designing has to be done. You know, most of the Intel's processors are going towards FinFET nowadays. So there also you need to have clocking strategies with more challenges. And many more challenges are there. In fact, it's a huge domain where a lot of research, a lot of industrial activity is being carried out. So you can think of taking up this problem in your career. So with this very brief outline, I would like to invite questions from you.
Hello, thank you very much, sir. So, any questions from participants? You can.
So there are two things. If questions are less or nil, two things that I have excellently presented, or I have not presented at all.
No, sir. So actually, it was fine, but actually, the particular topic based. So those are working on that, or those are interested in that.
Yeah, I understand. I was just
Excuse me, sir. No, sir.
Yes,
It is clear presentation.
Excuse me.
So
I have
Yeah.
that's why
Rohit.
you have no doubts.
Okay, Rohit Goel, sir, you can.
Hello. Hello.
yes, please.
It's a clear presentation, sir. That's why you have no doubts. Hello.
hello.
Yeah.
Yeah, I have questions.
Yes,
Hello.
please,
Yeah,
sir.
Rohit.
I have questions, sir. So when you are talking about that buffer and FIFO, then in that case you are talking about Placiocronus system, timing system. Is it similar to that?
See, let us plus synchronous, mesosynchronous, asynchronous. Let us not confuse about those things.
Okay.
Be very clear that when I am talking of a system which is having multiple clock domains, say there are 2 clock domains, my data is moving from domain 1 to domain 2. I have to keep both of them in sync with an objective
Right.
that I do not miss out data. So that's very clear. When I will tell you, friends, there are a lot of definitions given in the book regarding systems, but true industrial designers, they always see at a very elementary level.
Okay.
So now definitions, you match it. So systems are had to be properly synchronized either through some handshaking mechanism or through some routine mechanism. There are many ways of synchronization, of course, you have seen. And if you see in your books, they have different definitions for that. So what do you mean that it has to be, the sender has to give the information to the receiver that I have sent. The receiver has to give information to the sender that I have received. So this information can happen through handshaking or through automatic or through anything.
Any further questions from the participants?
I would like to request our audience to kindly put up any questions if they have any. They can directly ask to our research persons or they can pop their questions in the chat box. Sir, we have one question in the chat box. Mr. Ankur dropped the question. In multi-core architectures such as SOCs, how clocks are managed in software level to implement DVFS in order to reduce energy consumption of the system?
Okay, in multi-core architectures, SOCs, of course, are multi-core architectures. Software level means, what do you mean by software? Software has different meanings. To me, a software means design software. Are you talking of? Means like your design environment, design IDEs, or you can say integrated design environment, something like that you are talking of. If that is the system, actually we manage it with those software only. In the integrated design environment, so we generally do not do things in hand. There are many coding techniques where we manage those things actually. To reduce energy, see, actually in the RTL level only we change things. We don't insert a gate just like that. We RTL level. When you talk of RTL level, then of course it is managed in the software only. I don't know whether I have made myself clear or.
Sir, excuse me, sir.
Yes, please.
Again, sir, Mr. Ankur, he again dropped one question like.
Okay. So here, please, I could now read it out. No, sir, in OS level like Raspbian for Raspberry Pi, right? See, when I am talking of SOC, I have generally I have one operating system putting in Raspberry Pi. Raspberry Pi is actually a processor. So in my processor, if I am putting an operating system, when I talk of multi-core, there is one core will operate with a single frequency. So that is well known. And we have to see our system has to give only clocks to that. So in OS level, we have very less scope to do that. In OS operating system level, very less scope. It is actually in the design level of SoC. Whatever I want to do, I can do while I am designing the Raspberry Pi processor itself. And after that, I have only option to give clock to the Raspberry Pi. But managing the clock with operating system has very less scope.
Dear audience, do you have any further questions?
Yeah, okay, ma'am. I have a question. Sir, regarding the particular clock we are discussing, that is valid for that physical design point of view. That suppose you are going to any physical design of any IC or any design or testing anything, that static time analysis or that particular clock, this is going to relate or what?
You are right. Actually, static time analysis is done after. See, it is an integral. It's a part of that. Static time analysis is one part of that. We give the clock, then with respect to that clock, we carry out the static time analysis. But when I am talking of clock management, how do I supply clocks to different blocks so that there is less sleep? So, in fact, we get assured through static timing analysis, these things. So, it is mostly on the physical level of the system design.
Okay, sir. Thank you, sir.
Most welcome.
Any questions from audience?
Sir, one question, sir.
Sir, please.
Yeah, sir, when I designing a circuit, whether we should go for asynchronous design or we should
Dear
use for
audience,
multi-phase clock, which one will be
do you have
better,
any
sir?
further queries?
Okay. Whether asynchronous design is better or use of multi-phase clocking is better for a design. Sir, generally we go for, we discourage asynchronous design. We would love to have multi-phase clocking. Asynchronous designs, the systems really become independent of each other. If in a SoC there are two blocks and we make them asynchronous with respect to an asynchronous protocol, then systems become very much independent. And when systems become independent, they reduce the performance of the system. So, multi-phase clocking systems are done most of the time.
Thank you, sir.
Welcome.
Good afternoon, sir.
Good afternoon.
Sir, I have a question.
Please.
Sir, whenever we are designing something, let's say ASIC, so we have some block like a special handling block like boundary scan, clock generator, and asynchronous block and core. So whenever you are taking this in a design, particular design, so how to do the clock management with this? Which trick is applicable for this?
See, you told a couple of things. One is boundary scan. Boundary scan is done for insertion of DFT. Design for testability is a part of design. There we have a different clock, obviously. And other parts are there. So these blocks you can think of as different parts of your SoC. And whichever part is requiring whatever frequency, We have to give it to that. We have to generate those frequencies. Most of the times the DFTs frequencies are not highly linked with the normal path frequencies. But anyway, clock has to be given. The clock skew in the DFT boundary scan path has also to be minimized. Clock skew, clock jitter, everything has to be accommodated in all parts of the design. So, if it is complex design, then multiple clocks to be generated, then you have to derive the clocks from a one clock source all the time. It is not that in an SOC there are say 5 different frequencies required. I give 5 different crystal oscillators. I give only one crystal oscillator. Other clocks I derive out of that. So such things are very much done. If you have anything else, I can, whether I have answered you or I did.
Yes, sir. Actually, sir, whenever you are designing that separate auxiliary logic, like some pad rings and some clock generator, some boundary scan, I'm talking about inside a ASIC. These are the parts like boundary scan, clock generator, and asynchronous logic. These are special handling and some initial pads like just like some buffer and some synthesized core like core. So that whenever you are applying the clock, simultaneously you will apply same type of clocks or you are applying different types of clock?
See, in the design phase, there are different phases. First phase is that you are testing individual clocks, then you have to give individual clocks. But once it is integrated, it has to be in sync. You cannot have multiple sources of the clocks. Same source clock will be there, and wherever whatever is required, you have to derive. Like I was giving in one of the processor, there is an example. There is a core clock, there is a IO clock, but both are derived from the same clock source.
Sir, one other question here. What is the use of asynchronous SRAM from Sibram Mansoor in the chat box?
Okay. SRAM is generally in asynchronous. It's actually the batch write operation, read operation, FSMs need to have some clocks. So asynchronous, the SRAM memory is there, and then generally we use them for least access memory type. Whenever we want some information to be derived, then asynchronous SRAM is used generally. If it is a frequently accessed, then it has to be properly synchronous.
Okay, thank you, sir. I think there is no question more. So thank you for the particular topic, and those are research scholars working on the particular topic. They are much more relevant to the particular topic. It will benefit for them. And regarding, I found something that is also related to the industry point of view, because in the PD, that main thing is that that chief and all this clock analysis is very much important. And that point of view, I think it is a nice topic for all the research scholars and the faculty members present here. So once again, thank you very much, sir.
Thank you very much.
Okay, sir. We'll wind up the session here.
Okay.
I will talk you offline. Thank you, sir.
Okay. I will log out.
Yes, sure, sir.
So thank you all.